Hi, my name is Sam Olds. I am a software engineer here at Cisco. Um, so I'm flashing this up on the screen. This should be where you land if you follow that QR code that Anit shared earlier, but we can also share this link, I'm sure. But this is the compiler code is available. I've been working closely with the team to operationalize all of the research that Anit has been talking about into a developer-friendly toolkit. It is a Python-based thing, taking a lot of feedback or intuition from Qiskit. Qiskit's been a great example for us. So once you get your file download, once you have downloaded it, you can pip install QNDK, and then many of these things that Anit have been talking about are available for you to play around with in your local development environment. So I'm going to start off with just kind of the basic flow, talking about the pipeline that Anit was showing, taking us through initializing a quantum circuit, setting up what your data center topology and characteristics look like, doing the partitioning and the mapping, and then running a simulation and doing an analysis on the results. So this first example, we're just going to use a Qiskit circuit, a kind of simple toy example like Anit was showing. Just a couple of CNOT gates over 8 qubits, and then we're going to define what our topology looks like in our data center. So here in this example, we're going to do the class topology, and I'll talk about this more later, but this is how you would define the hardware characteristics in of each of the nodes in the topology. So here's what this topology looks like. These are top of rack switches. These would be the near IR switches. These ones up here would be the telecom switches. And then there's basically one QPU per server rack. And in this example, each QPU has a total of 4 qubits. So next we are going to use the window-based circuit partitioner Anit was talking about, and we're going to partition up our circuit that we had defined, and we can see how it gets mapped into our data center here. It is going to span across these 2 different QPUs. But again, like Anit mentioned, we want the partitioning to be intelligent. You want to keep logical groups of qubits that have a lot of interaction with each other local. You want to maximize your local gates and minimize your non-local gates. So this partitioning algorithm will do that. And then we enter the scheduling simulator step. And here we're going to plot this. This will basically step through the circuit and analyze any sort of network operations that are required to execute that circuit distributedly. And then you can plot what the shared network resource usage is over time. So in this case, these are Bell state measurement readings that are taken over time. So in the first execution step, there's one Bell state measurement reading that was required, which indicates the number of entangled pairs that are needed to perform that non-local gate. So if we were to switch up what our topology looks like a little bit, keep that same circuit that we were using earlier, repartition, map it back onto the topology. Here, there's going to be many more non-local operations. And so we can resimulate it and see kind of how the shared network resource usage over time is impacted. So the next thing I want to dive into a little bit is taking a little bit of a deeper look at the circuit and how the circuit gets partitioned onto the network and what's happening at each of those execution steps. So we're going to reuse this same circuit here, and we're going to plot it onto this kind of topology. So here, again, there's going to only be 2 QPUs, 8 qubits total. So there will be some non-local operations in this specific example. And here, this is a directed acyclic graph. This is another representation of the series of operations that happen as the circuit is executing. So each of these green nodes are a qubit. The blue ones are the gates that are happening between the qubits. And Qiskit does a good job of having a representation like this, but we've enhanced it a little bit further with the network events that are happening. So right here at this node, this must be a non-local gate, which means that there is an entangled bit that would be required, which means that at this switch, a near infrared switch, there'll need to be entanglement generation that happens before this operation can be performed. So if we were, again, just to kind of drill down onto that example a little bit, look a little closer at a different topology that has a lot more of those non-local gates, we can see there's going to be a lot more non-local non-local gates, more EPR generation that's going to be required. So this can kind of give you an idea. If you want, you can look at this like exact execution log. I want to emphasize that we are using Qiskit in this example to define the circuit, but we also support Chasm. You can use Chasm instead. And then we have our own simulation engine under the hood that's what's actually stepping through these circuits and analyzing what events are happening, where in the network are they happening. So if I run this example, the interactivity on that other plot is not working right now, but we can step through. So here, this QPU has 8 qubits in this example, and there's 8 qubits here. And so there's this interactive graph that'll show you at each execution step in the circuit which network devices are involved in that. So everything fits onto one QPU here in this example. But if we split it up so that there's only 1 qubit per QPU, now we can see all of the different nodes involved in each step of execution in the network and get a better understanding of maybe where bottlenecks would be in our network and how we might want to structure things differently. Okay, so we talked about the circuit. You also want to be able to define your network, your topology, and play around with different structures, different things. For this example, I'm just going to pull in a 8-qubit QFT. And he had showed us the B-cube topology earlier, which you could use if you'd like. That's kind of what this B-cube topology looks like. But we are going to go back to the class topology here. So you can define, the number of ports per switch, the number of QPUs per rack. Most of these toy examples have been a very small number of qubits, but of course you could push this up to 147 or whatever the kind of current state of the art number of qubits is, just to match your data center or whatever you're trying to test. But then the other important part of this is defining the hardware characteristics of each of the nodes in the topology, and this is how you do that. So you would take your topology, whatever you have, and you would define. Right now, these are just kind of doing the default values for different characteristics of the QPUs. So there's a certain number of communication qubits, the bandwidth that exists in each of the links, the number of entanglement sources or Bell state measurement modules that exist in the near infrared switches or the telecom switches. And this is a little helper method to create a homogeneous network, but you can create a heterogeneous network if you want, where all the different nodes have different types of characteristics, and run it through the simulation. It will respect these shared network resources, and you can plot what those shared network resources look like over time, like I had showed earlier. So here, if we want to, just another quick example, change some of these values, and just rerun it a couple of times, same circuit, same topology, but with just different amounts of communication qubits, for example, we can take a look at how that impacts these shared resources over time. Next thing I wanted to highlight, again, this is a Python SDK. So we want to provide a lot of different tools that you can pull down off the shelf and use. But if you have something better that you want to use, you have the ability to extend these different classes, these different functions, and use whatever you want to use instead of whatever we're providing. So here, I'm going to use another QFT on the class topology, but I'm going to write a custom partitioning function. So this partitioning function is kind of silly in practice because this is just doing round robin. You want to minimize your non-local operations and maximize the local operations, and this is not doing that. But It's pretty easy to extend the different modular components of this. We're trying to make sure there's a nice, consistent interface between each of the modules so that you can plug things in as you want. And then you can still just run it through the remaining steps in the pipeline and run an analysis and get an idea of how well that worked. And the last thing I want to talk about before handing it off to Adam is all of these examples so far have just been really small toy examples, just a couple of qubits, a couple of CNOT gates. But this is an example just pulling from Qiskit of a hydrogen molecule simulation. So if we run this, this is just regular Qiskit, and then this is what that circuit looks like. It's quite involved, quite a bit to it. But it doesn't change anything in the rest of our pipeline with QNDK. You can still just define your topology, your partitioning algorithm, all the different things that we've been talking about so far, and see how it gets mapped onto your network and run an analysis of how what the network latency might look like. So in this case, we had showed the Bell state measurement module readings over time. That was just kind of at an arbitrary time unit execution step. But here we have another way you can define the different constant kind of values in your network, the generation, the near infrared entanglement generation probability, switching delay, qubit reset, things like that, and then run a network latency estimator and see how well it does. And so here's just another example of just kind of changing these values a little bit to something that matches more closely what you're working with, and you can replot it and get a better idea of what's going on.